Good morning, students. Today we will learn dimensional analysis, which comes in the second chapter of +1 physics. And we will be seeing what are dimensions of a physical quantity, how to find the dimensions of a physical quantity, and then we will see the units and dimensions of some physical quantities which you study in +1 and +2 physics, and also see some quantities having the same dimensional formula, but they are different physical quantities. Then we will go to the applications of dimensional analysis and see how to check the dimensional consistency of an equation, and also see how to deduce the relation among physical quantities. And finally, we will see the limitations of dimensional analysis. So let's begin. So what are dimensions of a physical quantity? You know that all physical quantities can be classified as fundamental quantities and derived quantities. And you have already learned about 7 fundamental quantities, which are mass, time, length, temperature, luminous intensity, amount of substance, electric current. So all these 4 are fundamental quantities, and any other physical quantity in the universe which can be derived in terms of these fundamental quantities are called derived quantity. Now, if Q is a derived quantity, it can be expressed by Q is equal to m raised to A, L raised to B, T raised to C, where m is the mass, L is the length, and T is the time. Here, m raised to A, L raised to B, T raised to C is called dimensional formula, and the exponents or powers A, B, and C are called the dimensions. So any derived quantity can be expressed in terms of mass, length, or time, and other physical quantities which are fundamental in nature. And their powers, how many times mass comes in that equation, and how many times length come, how many times time come, are their exponents or powers A, B, and C. They are called the dimensions of the physical quantity Q. So let's see how to find the dimension of a physical quantity. Example, force. You already know the equation that force is equal to mass into acceleration. F is equal to ma. One point to be noted is that if you want to find the dimension of a physical quantity, you need to know its formula. You need to know how to define that quantity, what are the things on which that physical quantity depends. So this is a simple example where we find the dimensions of force. You already have learned force is equal to mass into acceleration. So mass is a fundamental quantity. You can express it as m, but acceleration is a derived quantity and can be expressed in terms of the fundamental quantities. For example, acceleration is velocity divided by time, right? And velocity is displacement divided by time. Displacement means a length. So L divided by time, T. So L T raised to -1 will be the dimension for velocity. And for acceleration, velocity divided by time. So again, one more T raised to -1. So the dimension for acceleration is L T raised to -2. Now we put these quantities in this equation. So using 1 and 2, we will get F is equal to, for M, we have put the dimension capital M. And for A, we have put L T raised to -2. Note, whenever we are expressing the dimensional formula, we always put a square bracket. Not the curved brackets, always the square bracket. So we got the dimensions of force. This is the dimension of force. I hope it is clear. So similarly, we can find the dimension of any physical quantity if you know its basic equation. So now let us see some of the units and dimensions of some physical quantities. So here we have the physical quantities, units, and their dimensional formula. So first of all, acceleration. Acceleration or acceleration due to gravity. You remember acceleration due to gravity? You learned in the chapter gravitation, and it is expressed by the letter G. On the surface of Earth, it has a constant value 9.8. So both acceleration and acceleration due to gravity have the same unit and same dimensional formula, because both are acceleration. So we saw acceleration means velocity by time. Velocity is displacement by time. So LT raised to minus 1 divided by time, it will be LT raised to minus 2. And it has a unit meter per second square. Now angle. Angle is derived as arc by radius. So in SI unit, angle is equal to arc by radius. Arc is a length. Radius is also a length. So length by length, it will cancel. So it doesn't have any dimension. If there is no dimension, you will express the dimensional formula as m raised to 0, L raised to 0, T raised to 0. Anything raised to 0 is 1. So m raised to 0 is 1, L raised to 0 is 1, T raised to 0 is 1. So what remains is just 1. It doesn't have any dimension. So angle is a dimensionless quantity. You can sometimes represent the dimensions of a dimensionless quantity as 0, 0, 0. That is m raised to 0, L raised to 0, T raised to 0. Then comes angular displacement theta. Angular displacement is also an angle. So it also have the same unit radians, and it has the dimension m raised to 0, L raised to 0, T raised to 0. This must be big letter L. This is a typo. So angular frequency. Now what is angular frequency? It is angular displacement divided by time. You know, angular displacement doesn't have any dimension. So divided by time. Divided by time means T raised to minus 1. And it has its unit angular displacement divided by time. So radius per second. Radians per second. So angular impulse. Angular impulse means torque into time. What is torque? Torque is force times distance. Force we already saw, it is m L raised to L T raised to minus 2. M L T raised to minus 2. We have already derived the expression for force. So torque is force into L. So it will come as m L square T raised to minus 2 into time. So into time, m L square T raised to minus 2 plus 1, which is minus 1. So we will get the final expression as m L square T raised to minus 1. And its unit is Newton meter second. Newton means force. Newton meter is torque, because torque is force times distance, or displacement times force. Time second. So this is the unit for torque times time, angular impulse. Then comes angular momentum. Angular momentum also has the same dimension as angular impulse. Also remember that impulse and momentum has the same dimension. Both of them have the same dimension. Similarly, angular impulse and angular momentum has the same dimension, ml square T raised to minus 1. Then angular velocity. Angular velocity is again angle divided by time. Angle, you know, it doesn't have any dimensions, and time is divided by time. So T raised to minus 1. So angular velocity has a dimension T raised to minus 1. Then area. What is area? Length into breadth. Length is a length. Breadth is also another kind of length. So the dimension of area is L square. Now, can you guess what will be the dimension of volume? Volume is length into breadth into height, right? So L times L times L, which is L cube. So the dimension for volume will be L cube. Now let us see more physical quantities like bulk modulus. Bulk modulus is also a kind of pressure. It's a type of pressure or change in pressure. So it has the same dimension as pressure. Pressure is force by area. Force is mLt raised to minus 2 divided by area is L square. So L will change. Instead, L by L square will be L raised to minus 1. So bulk modulus is m raised to 1, L raised to minus 1, T raised to minus 2. Now, coefficient of viscosity, it has a dimension m, L raised to minus 1, T raised to minus 1. Note, here you can write m or do not write m. It doesn't make any difference. Either you can write m or just m raised to 1 or just m. Both are same. Then compressibility. Compressibility is 1 by bulk modulus. We already know the dimension for bulk modulus. It is m L raised to minus 1, T raised to minus 2. So bulk modulus reciprocal compressibility. So you have to put instead of 1, minus 1. Instead of minus 1, 1. And instead of minus 2, 2. So you just took the reciprocal of this dimension and you got m raised to minus 1, L and T square. Then density is equal to mass by volume. Mass. So m, and we already deduced the dimension for volume, which is L cube. So m, L raised to minus 3 because volume comes in the denominator, L raised to minus 3. Then displacement, wavelength, focal length. All of these are some kind of length. Displacement, change in position. So it's a length, wavelength, the distance traveled by a wave. So it is also a length. Focal length of a lens or a mirror, it's also a length. So all of this are length. So it has the dimension L. Now force constant or spring constant, it is force by extension. Force we have derived earlier, mLt raised to minus 2. Extension is the distance moved by the spring or anything like that. So it's a distance or a length. So divided by L. So L gets cancelled and you will get mt raised to minus 2. There is no L. So mt raised to minus 2 is the dimensional formula for force constant. Then frequency is 1 by period. Period means time. So 1 by time. So t raised to minus 1. Then gravitational potential is work by mass. What is work? Force into distance, right? So we have force mLt raised to minus 1 into L. So work will be mL square T raised to minus 2. So force work divided by mass will be, mass gets cancelled, L square T raised to minus 2. That's it. Now heat. Heat is a form of energy. It has the same dimension as that of work. So like before we told that work or energy is force times distance. So mLt raised to minus 2 times L, which is mL square T raised to minus 2. Then illuminance, it is mt raised to minus 3. Impulse is force into time. Again force. So you remember the formula for force. It comes several times. So once you know the dimensional formula for force, it is easy to derive the dimensional formula for many quantities like force constant, work, energy, impulse, etc. So force into time. Force is mLt raised to minus 2 into t. So you will get it as ml t raised to minus 1. So you can also find the dimensional formula for many such quantities. Now, quantities having the same dimensional formula. There are several physical quantities which has the same dimensional formula. And you may get multiple choice questions out of these, which of them have the same dimensional formula, or you may get match the following type of questions, or you may get questions which say the odd one out. So you will have to pick up the quantity which has a different dimensional formula from others. So for all such questions, the knowledge of quantities having the same dimensional formula will be very useful. So impulse and momentum have the same dimensional formula. Work, torque, the moment of force, energy, they have the same dimensional formula. Let us consider impulse and momentum. Impulse is change in momentum. So it should have the same dimension. What is impulse? It is force times time. Force is ml t raised to minus 2 into time ml t raised to minus 1. Similarly, momentum, mass into velocity. M for mass, velocity is L t raised to minus 1. Displacement by time. So both are same, impulse and momentum. Now, work is force into time, force into distance, and torque is perpendicular distance into force. It's also distance into force. So it has the same dimension as work. Now, moment of force is another word for torque. And energy is another, and work and energy are interconvertible. So they have the same dimension. So all these quantities have the same dimension. Then angular momentum, Planck's constant, rotational impulse, these three has the same dimension. Stress. What is stress? You have learned it. Force by area. What is pressure? Force by area. So obviously they have the same dimension. Modulus of elasticity. It is stress by strain. Strain doesn't have any dimensions. So modulus of elasticity has a dimension of stress. Also energy density has same the dimension of pressure, because energy density is energy by volume. So pressure is force by area. So they have the same dimensions. Now force constant, surface tension, surface energy, all of them have the same dimension. Angular velocity, frequency, and velocity gradient has the same dimension. Gravitational potential, latent heat of fusion, latent heat of vaporization, all of them have the same dimensional formula. Then thermal capacity, entropy, universal gas constant, Boltzmann's constant, all of them have the same dimensional formula. Force and thrust are almost the same. Thrust is some kind of force exerted by a liquid, so, or a gas. So it is also a kind of force, so they have the same dimension. Then power and luminous flux, they also have the same dimension. Now let us see some of the applications of dimensional analysis. Dimensional analysis can be used to check whether an equation is dimensionally consistent or not. So checking the dimensional consistency of equations. Let us consider the equation half mv squared is equal to mgh. What we have to do is we have to find the dimension on the left hand side and also on the right hand side. And if they are same, the equation is said to be dimensionally consistent. If an equation is not dimensionally consistent, it is wrong. So you can confirm that an equation is wrong if it is not dimensionally consistent. If an equation is dimensionally consistent, there is a possibility that the equation is correct. So let us see how we can do that. half mv square. So let us write the dimensions of LHS and RHS separately. So let us consider LHS left hand side, half mv square. Half doesn't have any dimension. M is mass, so m. This is dimensional formula for m within the square brackets. Velocity, displacement by time. So displacement is length by time t raised to minus 1. This is a typo error. So whole square. So you have to take the square of this. So that this will become m. When you take the square inside, it will become L square t raised to minus 1 into 2 minus 2. So L square t raised to minus 2. So you will get the dimensional formula for the LHS as m L square t raised to minus 2. Now let us consider the right hand side. mgh. M is mass, g is acceleration, velocity by time. We already have here the dimension of velocity, Lt raised to minus 1, by time. So one more negative 1. So it will become one more. So t raised to minus 2. So acceleration g. I told you g is a acceleration due to gravity. It's a kind of acceleration. So it has the same dimension as that of acceleration, L t raised to minus 2. H is height. It's a kind of length. So L. So you have the together m L square t raised to minus 2 because L comes twice here. So L square t raised to minus 2. See, both of them are same. So we can say that the dimensions of LHS and RHS are the same. Hence, the equation is dimensionally consistent. You may get a 2-mark question like this for your +1 examination because this belongs to the focus area. Now, another example where we check the dimensional consistency of the equation. The difference here is that in this equation, we had only one term on the left-hand side, one term on the right-hand side. What if there are more than one terms? We have to check whether the dimension of each term is the same. So here we have 3 terms. This is S, one term on the left-hand side, ut, another term on the right-hand side, half at square, another term on the right-hand side. So we have to take separately the dimension for each term and then show that they are the same. What is S? Displacement. So its dimension is L. What is ut? U is the initial velocity, t is time. So for u, we can write L t raised to minus 1. For time, you can write t. So L t raised to minus 1 into t. So minus 1 plus 1, 0. So there is no t here, only L. Now let us take half at square. Half at square. Half doesn't have any dimension. It's a number. Then A, acceleration. So L t raised to minus 2 into t square. So t square. So minus 2 plus 2, again 0. So what remains is L. So here you have first term L, second term L, third term L. So all 3 terms have the same dimension L. So this equation is dimensionally correct. So this is how we can check whether an equation is dimensionally consistent. So this can be another 2-mark question. Now, another application of dimensional analysis is that it can be used to deduce the relation among physical quantities. Let us see an example. Derive the formula for centripetal force F acting on a particle moving in a uniform circle. The centripetal force acting on a particle moving in a uniform circle depends on its mass m, velocity v, and radius r of the circle. Hence, we can write force F is equal to mass raised to a, velocity raised to b, radius raised to c. So force may depend upon mass, velocity, and radius. We do not know what is A, B, and C. We just put some quantities A, B, and C. Now we have to find out what is A, B, and C using dimensions. So when you are asked such a question, they will tell you what are the quantities on which the centripetal force will depend. So don't worry, this much will be the part of the question. So they will tell, find out a possible equation for centripetal force, which depends upon the mass, velocity, and radius. So let us write the dimensions on both sides of this equation. Force, you know, it is mLt raised to minus 2. Mass, m, so m raised to a. Velocity, v, is L t raised to minus 1 raised to b. And r is radius, so it's a kind of length, L raised to c. Now let us expand this side of the equation. This side we have written it as such. Then m raised to a, b goes into the bracket. So L raised to b and then L raised to c is there, right? So L raised to b plus c. L raised to c plus b, which is same as b plus c. T raised to minus 1 whole raised to b. So t raised to minus b. Minus 1 into b is minus b. So we got the equation. Next step is we have to compare the powers of each of these, m, L, and t. So power of m here is 1. Here it is a. So you can write a is equal to 1. Then here power of L is 1. Here it is b plus c. So you can write b plus c is equal to 1. Here power of t is minus 2. Here power of t is minus b. So you can write minus b is equal to minus 2. So b is equal to 2. So from this expressions, we can find a is equal to 1, b is equal to 2. Now, if you put b is equal to 2 in this expression, you will get 2 plus c is equal to 1. Or c is equal to 1 minus 2, which is minus 1. So c is equal to minus 1. Hence, the centripetal force can be expressed as F is equal to K is a constant. So there may be a constant, we do not know. So we'll just write K, a constant. We always write that. M raised to, instead of A, you have 1. So instead of A, you are writing 1. V raised to, instead of B, you have 2. So V square. Instead of C, you have minus 1. So R raised to minus 1. And you know that R raised to minus 1 means divided by R. So F is equal to K mv square by R. K can be any constant. So we have deduced the expression for centripetal force using dimensional analysis. Let us see one more example where we are deducing the expression for time period of a simple pendulum using the methods of dimensions. So this can be a question for 3 marks. Derive the formula for centripetal force, which depends upon mass, velocity, and radius. This can be another question for 3 marks. Time period of oscillation of a simple pendulum using the method of dimensions. So here they must have given in the question itself that time period may depend upon the mass of the pendulum, length of the pendulum, and acceleration due to gravity. So we can write T is proportional to m raised to x, L raised to y, g raised to z. L, x, z are unknown quantities which we have to find out using dimensional analysis. Or you can write T is equal to a constant k, m raised to x, L raised to y, g raised to z. This is one equation. Now let us write the dimensions on both sides as we did before. There is only t. So you can write m raised to 0, L raised to 0, t raised to 1. We are writing m raised to 0, L raised to 0 because to the end, we will have to compare the powers of m on both sides. That's why. Then k is a constant, so no need to write any dimensions. M raised to x. Write it as such. L is length, so L raised to y. G is acceleration, which has a dimension L, t raised to minus 2 whole raised to z. So take z into the bracket. So it will be L raised to z, t raised to minus 2z. Now combining, for m there is no other m, so m raised to x itself. For L there is L raised to y and L raised to z. So L raised to y plus z. And for t there is no other t, so t raised to minus 2z. Now let us compare these two sides. So m raised to x, m raised to 0. From this we can say that x is equal to 0. Equating the dimensions on both sides, x is equal to 0. Y plus z, here it is 0. So y plus z is equal to 0. Here minus 2z, here it is 1. So minus 2z is equal to 1. Now if minus 2z is 1, z is equal to, taking minus 2 to the other side, z is equal to minus half. So we got x and z. To find y, we can put this z in this expression. So you will get y plus, instead of z, I have put minus half. Y plus half is equal to 0. So when we take minus half to other side, you will get y is equal to half. Now we got x, y, and z. We can substitute in this expression. So time period t is equal to k, constant, m raised to 0 because x is 0, L raised to half because y is half, g raised to minus half because z is minus half. And you know that anything raised to half means square root of. Anything raised to minus half means 1 by square root of. So combining that, you will get the final expression. Time period t is equal to constant k into square root of L by g. See, m is not there, which means time period doesn't depend upon mass. So even if we took a mass dependence in the beginning of the equation, by the time we analyzed dimensionally, we found that time period doesn't depend upon mass of the pendulum. So time period is equal to k into root of L by g. So we have deduced a possible equation for the time period of oscillation of a simple pendulum using methods of dimensions. So to make it clear, let us consider one more such problem. This can be a question for 3 or 4 marks. So example, suppose I have the following equation. F is equal to e raised to a, b raised to b, t raised to c, where F is force, E is energy, V is velocity, and T is time. So to find the relation between force, energy, velocity, and time, we have to find the values of A, B, and C. Let's do it using the dimensional analysis. We know that force is mLT raised to minus 2. Energy, same as work. So here into L will be there. So mL square t raised to minus 2. V is velocity, LT raised to minus 1. T is time, so T itself, no need to write it separately. So let us put all these dimensions in this equation. So you will get, instead of F, mLT raised to minus 2 is equal to, for E, mL square t raised to minus 2 whole raised to a, because here we put e raised to a. So the dimensions of e raised to a, dimensions of velocity lt raised to minus 1 whole raised to b, and dimensions of t, that is t itself, raised to c. Now let us put a into the bracket. So m raised to a, L square into 2 into a. So L raised to 2a, there is here L raised to b. So L raised to 2a plus b. T raised to minus 2 raised to a. So T raised to minus 2a. Here there is minus b. Here there is c. So T raised to minus 2a minus b plus c. Now let us compare. Here instead of a, you have 1. So a is equal to 1. 2a plus b 1. So 2a plus b is equal to 1. Minus 2a minus b plus c equal to minus 2. So we have these three equations. A, you already got it as 1. So if you put a is equal to 1 here, 2 plus b is equal to 1. B is equal to 1 minus 2, that is minus 1. So b is equal to minus 1. So put a is equal to 1 and b is equal to minus 1 in this equation. So you will get minus 2 minus of minus 1 will be plus 1. So minus 2 plus 1 is minus 1 plus c is equal to minus 2. So when you take minus 1 to this side, it will be plus 1. So c is equal to minus 2 plus 1, which is minus 1. So you got these three expressions. So let us put a, b, and c in our initial expression. So you got force F is equal to K. K is a constant. I told you always we put a constant because a constant doesn't have any dimension. So we don't know whether there is a constant in the equation. So we just put the constant K. It can be 1 or any value. So F is equal to K e raised to 1. A is 1. So E. V raised to minus 1 because B is minus 1. T raised to minus 1 because C is minus 1. So we got the final equation as F is equal to K constant. E, V raised to minus 1 means divided by V. T raised to minus 1 means divided by T. So this is the final equation. So this is how we can deduce an expression between force, energy, velocity, and time. Now let us see finally the limitations of dimensional analysis. Dimensional analysis check only the dimensional correctness of an equation, but not the exact correctness. As I told before, if it is dimensionally correct, the equation can be correct, but we are not sure it is correct. There may be a constant. There may be more terms with the same dimension. So we cannot be sure whether the equation is correct or not. Second limitation, while deducing a relation, the dimensional constants cannot be obtained by this method. As I told you before, we wrote in all the deductions a constant k. We cannot find out what that constant is using dimensional analysis because dimensions doesn't have any, constants doesn't have any dimension. We cannot deduce a relation if a physical quantity depends on more than 3 physical quantities. See, in all these deductions, we considered that force depends upon 3 physical quantities. Here, time period depends upon 3 physical quantities. Here, force again depends upon 3 physical quantities. So, if any quantity depends upon more than 3 quantities, we cannot deduce a relation. Means we cannot deduce relation if it depends upon more physical quantities more than mass, time, and length. What if it depends upon the luminous intensity? What if it depends upon temperature? What if it depends upon amount of substance like mole? So if the physical quantity depends upon other quantities, other fundamental quantities other than mass, time, and length, you cannot deduce the relation. A formula containing trigonometric, sine theta, cos theta, tan theta, they do not have dimensions. Exponents, they do not have dimensions. Logarithms, they do not have dimensions. So formula containing trigonometric, exponential, and logarithmic functions cannot be deduced using the methods of dimensions. So these are the limitations of dimensional analysis. I hope this video was useful to you. Wish you all the best for your +1 exams and also for learning physics further.